The next speaker is Guchuan Li. He's going to talk about profinite transfers and chromatic homotopy.
Yeah, thanks for organizing such a wonderful conference and having me speak, and thank you for the introduction and the interesting story. That's a good complimentary, because I learned that for a talk I should prepare some story, but I didn't. So I think my advisor saved me. Okay. So the talk is about profinite transfers in chromatic homotopy theory, and can be regarded as analogs of G homeomorphism. So maybe let's start with the inmate of J. So for this one, like there's a classical map from the homotopy groups of the compact Lie groups going into the stable homotopy groups of sphere. And I just learned the history, like both Whitehead are related to the J homomorphism. This is maybe the George Whitehead one, to construct the map. So then we can see the image of J, it's just the image of this map. And chromatically, this is detected by K1 local sphere. Maybe let me just state the result for the alt prime, and prime 2 is very similar, but something is off. So basically saying is the image of J is isomorphic to pi star of K1 local sphere, and if I start from the stem 1. And so this is studied by Adams using the Adams operation. So maybe if I'm writing in the chromatic names, so maybe this is alt and this is prime 2. I can define this K1 local sphere to be a fiber with some Adams operation you can choose. And for prime 2 case, you can start with KO instead of KU. And so we are in stable world, so we can desuspension once. And as you can see, the homotopy groups in the stable world, this is very much almost the same as the group of the Lie group there. So this is also can be thought as the image of J, or the J homomorphism. But in this case, the second one, this is the unit map for this ring map, for this ring spectra. And so like by computation, you can show this is actually the same as Spanier Whitehead dual of KO itself. Let me just do everything K1 locally. This is a K1 dual, which defined to be the home to the sphere, but now I take the dual in the K1 local category. And then the most obvious map for this one is this is just like the dual of the restriction, dual of the unit map in this case. And this is, it's Han, Michel. So they did the computation and showing that not only this is isomorphic to the dual, and this map is actually due to the unit map with a choice of the isomorphism here. And so in this week, we already see in chromatic homotopy theory, so you can fix a prime P local, and then fix a height. And then there is a very nice like E infinity ring spectra En. It means a nice action by Jn, like this, due to Gross-Hopkins-Miller and also has very nice interpretation and independent proof by Lurie. And I'm also being very vague for the choice of the morality theory or the looping theory here. The reason is we will compute like homotopy groups and image in homotopy groups. So the choice doesn't make much difference. So maybe I'll just fix the choice to be pick up a height n formal group law just over the coefficients at p to the n. And all the rest choices doesn't change too much if you are thinking the image of the pi star there. And so with this setup, you can rewrite the same map slightly different. So this one, this is a K1 local sphere, is also known as the fixed point for G1, which in this case is just Z2 cross or ZP cross in other primes. And so this star, you can also do an underline similar wording further out prime, can be regarded as the following map. So I'm just changing names. There's nothing mathematically happening. Where also I know this is a K1 local dual of E1 H demo 2. And from this point of view, this union map is just well, so maybe I should say this is the same as K1 local sphere, and this is true for all heights. So this is due to Devenaz and Hawkins. And this has a very nice interpretation as a pro-Galois extension. Like by Rognitz. So if I think in this way, this is just a restriction map. I have a very large group, and the fixed point maps into the fixed point of a smaller group, a subgroup in it. And then this is a dual of the restriction, and that's I want to call to be the transfer map. So then we have P, we have N, and now you can choose any closed subgroup in the morality splitter group, and consider the same thing, just as a dual of the restriction map. Let's just do the K local sphere for now. So this looks like some transfer map, but it would be better if this side can be written as a fixed point, H fixed point of the spectra star with En, and maybe with some shift number or some twist. So the goal of the talk is to first try to define a word of transfer of this format. You start with En and you twist, and then you take fixed point, and this one maps all the way to the larger group fixed point. And the second one, maybe let's see like a bunch of more examples, including the image of J, like in chromatic homotopy series. So I can vary the height, the prime, and also the close-up group to see this map does detect some interesting elements, like even like non-local, some products of beta family will show up in the later part. And maybe let me start with the first one. So then maybe let me start with a very specific example. So let me just choose this H to be finite. And now, for the upper one, I can cheat by means I didn't do the hard math. I just borrow hard math from my advisor's work, and then can change it into the second version. So in this case, I can start from the left-hand side, which I can just define this to be the Kn locals whenever I do of the restriction map from the k-local sphere to the ring spectra. And in this case, for the finite group, I have the Tate vanishing, or maybe like the new word, maybe the ambidexterity.
D is still K1 local D or?
Yes, thanks. Yes, like the Spanier ideal is always taken in the Kn local category. Yeah, thank you. And then, so the norm map is the equivalence. So I can Kn locally. So I can move this as an orbits. And then this is a home. This is a co-limit. Then I can put it outside. So now I'm much closer than the second part. And now use the Hart theorem.
Do you mean fixed points or orbits? I mean, you've shifted the H upstairs.
Yes. So the first step I used the Tate vanishing. These two are
You said
the second one.
Right. So what's going on the second one?
The second one. This is a home, and I regard this as a co-limit.
Right.
And then I put it out, became a limit, and then
okay.
so I can do the fixed point outside. And so yes, here comes the like a deep work by Ernest Bourdais, Paul Gors, Matt Hopkins, and Weisner, Janowska. So what they did is they actually identified the Spanier ideal of En, Moral E theory, like in the Gn equivariant D with the whole action. So this will be maybe with some shift. And of course, if I only care about the homotopy fixed point with a smaller group, I can just restrict their result to a smaller group. And then I have this gadget, looks very much like the upstairs format. Now I have a twins of the original object, and then I can map into that one. So maybe to see this one, is for this part is entirely independent about the E. It's only about the group. And this is defined by, in their paper, something special is you start with, or like it's not special, it's very general. Like you start with a compact p-adic analytic group. And you can choose a sequence of open subgroups here, such that all the interactions will be the trivial group. And well, with this property, like you can define the classifying space for the whole group to be the co-limit as I'm increasing the like these subgroups. But like I can entirely do this guy, and so I have a limit over the transfer map between all these open subgroup with finite index. And this is a definition in that paper for this one. But also, they did more. They compare this one with, so this one, the underlying is just a sphere with the dimension. This dimension comes from the common dimension of the group. And so this one can be equipped with the action from the Li algebra there. And they actually compare this one to the sphere with the one-point complexification of the Li algebra. Like for finite groups with properties that the intersection with the center is elementary P group. And Dustin Clausen announced the proof in full generality. So this is just as a Gn sphere, this is of this action. So that's a very special case. Like I can do this one. So maybe let's see what I can do for, or why this will be the written, why I can just take the Spanier ideal and
Sorry,
That's,
can
yeah.
I ask, like, can you think of this limit also as some kind of finite limit? I mean, I know that you have lots of finite index subgroups, but
Yes.
is there a way to, because you're compact or something?
Yeah, I don't think so, because you have to intersect the infinite to have the trivial group. That makes sense. Otherwise, if there's some finite properties, you're only doing the finite index transfer.
So it has to be infinite.
Yes, at least for maybe like the authors can have more insights.
There may be a
I
different
mean, the reason
thing
why
that it is a finite.
I'm asking the dual situation we discussed, we can actually open the root of the finite limit.
There may be something else, but not indexed on that.
Okay, I see.
thing.
Yeah. Thank you.
Yeah, so yes, and then we will see that this actually like the infiniteness does occur. Like so maybe yeah, let me
Can I just ask about your case? You were pointing at this, and I could tell what you were pointing at. So you get an S minus, the underlying spectrum is S minus n squared. Is that the I sub G?
yes,
And then you have an I sub G inverse, right?
yes.
The super.
Yeah, this turns out to be an invertible object, and like it's twins by the.
So it's the inverse. So the thing that appears in your formula is the inverse of the thing.
Yes.
That you have underlined. Okay. Thank you.
Yeah. Oh, sorry. Maybe then like the SG should be dimension n square. Yeah. Yes. So this is the same as S minus G. Yeah, you put the psi. Well, sorry. Let me see correctly. So IG itself is a sphere, representation sphere of the Lie algebra, and it's of dimension n square. And here the twins, I wanted the inverse of it. So its underlying is minus n square. And the action is just the same action. Yeah, thanks for pointing out the mistake. Yes, so, right, and so now like the case is we want to define the transfer. So maybe let's not be the ambitious to do this one. Just reveal what happens for the finite group. Now, like even with G, the whole group is finite. So in this case, well, you can take the G spectral or just take the G representation. And you do have the restriction map, and you have both side adjunctions to be the induction and the co-induction. And in the finite group case, you have very concrete constructions for them. And so if you take this setup, so then like you can see the, maybe, since it's giving a talk here, maybe let me try to follow the 6 functor formalism, if I can, to follow the minor here. Although like typically I will just do this one. So like you can imagine, think of the map from the classify space BG to BH to BG. And also this object with G action can be regarded as a shift over it. So in this case, the restriction is just at upper star, and then the formalism tells you there's a right adjoint. And then if you have more than 6, you have 7, then you will have the left adjoint to be the induction. And you will have also a more mysterious one, like concerned about the compact supported cohomology or homology. But we are safe in the case this everything is compact, or it's finite, so it's empirically compact. So in our case, all the F lower star and Schrick agree with each other. And so you have this minor of the functors here. And so you can also think about the map going down to a point. And in particular, this will just take the homotopy fixed point of your spectra with respect to the group you start with, and also it's a group cohomology if you're doing algebra. So in this format, like you have the restriction and the transfer. The restriction is a unit map for this junction pair, and the transfer is a junction for this pair. So if you check where does this scene lies in apply to a category, this all G spectra. So to have the map I write on the left-hand board, maybe I take the G fixed point, as I just mentioned here. I just apply this functor here. And now you will see the more familiar one. So the left-hand side is just, I'm taking the homotopy fixed point of my spectra. And the right-hand side, I take this one. But I recognize, like if I do F first, and I then do PG, there's a community diagram that's just, I'm taking the H fixed point now. And the other one is I restrict to the H level. So this is just saying I restrict my spectra to only remember the H action, and I take the fixed point. And this familiar version. And of course, you can do this one. And in this case, it's very easy because this shrink is star, upper shrink is upper star, so nothing happens. But like that's something also non-trivial. The seeing the induction and the co-induction agrees in this setup. And that also has a name, like the Wuth-Muller isomorphism, or the ambidexterity in the representation theory. Ambidexterity. So then, like maybe if you think about the compact Lie group, then you also have a Wuth-Muller isomorphism, where the twins did show up. So this is just saying the induction now, like G is a compact Lie group, and H is a closed-up group there. You see, the induction and the co-induction also differ by something invertible, and this one is a representation. It's a tangent space on G mod H, or at the union point. So this is a classical result, and if you put in that format, this is just saying, well, this turns out to be this guy. Well, there's a formal property which is isomorphism. This is the non-trivial part, and so in the setup of the sixth functor, this can be so this is a left adjoint to F upper star, and this is also, well, in this case everything is closed, so its proper is F lower shrink. It's also left adjoint to the F upper shrink. So you can imagine, if you have a relation between these two, you also have a relation between their junctions, also differ by a twinst. So then this one can be implied by the isomorphism here. And well, in the setup of sixth functor formalism, this is something like you will ask if you want something like cohomology smooth, or in the classical case, it's just asking for a Poincare duality for your group cohomology. And this thing, once you have the Poincare duality, you will have a similar isomorphism in this case. So since this is very like the case on the left-hand board, and you really want to just copy everything. And here comes back to the question, why something finite does not work. So the difficulty is, like in the compact Lie group, if I'm thinking of the same diagram, everything is still proper. And if I'm starting with a nice compact Lie group with a punctuality duality itself, then that's saying both this map are smooth. Because taking the F lower star for this map is just taking the group homology and there's a punctuality duality. However, the point is this is not smooth. And the reason is exactly as you expect, because G mod H is not finite.
Are we doing compactly or periodically now?
Periodically now. Oh, maybe I should emphasize why the difficulty of the periodic case. Like the warning is in this case, which is very different from the difference between the periodic case and the compact case is this one is not smooth. In the sense that if I have a smooth map, like maybe like the thing you wanna the pullback is still smooth. But this one, this is infinite dots, and the topology here is discrete. So if I'm computing the homology for this one, there are infinite dots, and it's not finite, it's not dualizable. So at least in this sense, it's not smooth. Does that make sense? Or yeah, please.
Why would G mod H carry the discrete topology rather than G mod H has a topology, right?
Oh, yes, you want to put the periodic topology there, right?
Yeah.
I think you're trying to say totally disconnected or something like that.
Yes, I think, sorry. I think the correct word is totally disconnected. No, I'm sorry.
Not discrete.
Yeah, sorry. Yeah. Thanks for the correction. Yeah, I think I said something entirely wrong, and the correct word is totally disconnected. And as a consequence, it's saying still like the homology is not like finite. So it cannot be dualizable. In this sense, like you just see whenever this map is of infinite order, you cannot do anything like that one because you don't have the isomorphism there. And so that's the reason like why you could not have some transfers for like infinite index. Yeah, and now let's see what we can do for this map. Of course, we already have candidates. So let's back to the example case, like you can do it in more general. If I have a closed subgroup, I can take the spaniel ideal to define a map. And now, on the left-hand side, although I don't have the isomorphism here, I do have a map from the left-hand side to the right-hand side. And I can still start with this gadget, and I can take the G fixed point. So the only thing different between from the compact case is this is no longer isomorphism, but still I have a map goes to it. So then after this one, you can play the same game over there. And all the rest are the same. So you will have something like E tensor something, like presumably will be invertible. And you take the H fixed point, and you go to the larger group. And this is a transfer, and also you can check. So with conditions either, so this formula, like there's a very easy case, you know this is true. This is true for 1. If I plug in 1, then this is of course true. And so you can imagine this is well true for the subsect category generated by 1. And if you do a little bit more hard, this can work for all dualizable objects. This will be true. So here, like once you have those conditions, you can check this exactly coincides with you just take the duality in your category of the restrictions. And also, like in the case, when you have the left adjoint, the F lower sharp, you can also check this one coincides with the definition upstairs. So this is a definition we propose, and since already like half of the time passed, maybe in the half of the time, I wanna maybe let me stop here for any questions so far or any comments.
So what is F upper shriek of 1? Is it like a space of distributions?
Yeah. Yes, so that's a very good question. In general, I don't know how to describe this one very well, but later on in the example cases, this is very concrete. And so what is known is like the PJ upper shriek 1 is known. That's the thing's result. Yeah, and this is fit into some fiber sequence or co-fiber sequence into it, but I cannot describe it very well. But like I will describe something very well in an example, so that may help. Any other questions? Yeah. So now, like,
I have one more question.
yes. Well, thank you. Like, yeah.
I mean, there's a six-functor formalism that from like the world of diamonds and stuff, and that's already in place. And I'm just wondering, is this a theory agree with the theory that was already?
Well, these are fantastic questions because that's what I'm trying to.
Because like I've done work in this subject.
Yeah.
Is this the same stuff?
Yes, that's a perfect questions. I think, yeah, like if you don't ask it, I may just miss the point, forgot to mention this point. So I think all I'm saying, I'm really cheating because I didn't set up the six-functor formula at all. I'm just like, lying say there is such one. And I think the one I'm working with currently is now going to the diamonds, that fancy, but I'm.
Yeah, and this is you wouldn't need to, but.
So I'm relying on. Yeah.
So can I ask you more questions? Oh, sorry, maybe answer.
So maybe then let me just say, here and man work out this like fantastic six functors for profinite groups with discrete coefficients. But so this is similar to if I'm working with complete ZP module. This is just once I do complete, this is a limit of ZP to the power k module. So I can pass from the discrete case to the complete world. And what happens is Kn local category is automatically complete with respect to the ideal. And I think Harvey and Strickland construct a sequence of generalized Moore spectra. This is just something like of the format. If you take the co-fiber of P to some power and V1 to some power, like by a theorem, like by Hopkins and Schmitz, like the nilpotent theorem, like you can, as the AI goes larger enough, there always such a map exists. So I can take the sequence here. And I can ask for the ideal all the AIs goes to infinity. And this will put a topology at least on all the homotopy groups. And but then later on, Berkeley showed that all such guys, when these powers goes larger, has some EK structure as a ring. And the K can also goes to infinity. And so based on this work, in a previous doing work with Guchuan, what we did is, so it's just the same story as here, the top line, and now the Kn local category. It's a module of the Kn local sphere. Where this sphere can admit such adic filtration. It's just like saying like R is a limit of R, then the complete R module category, the same as the limit of R module category. So everything can make into a categorical version. So there is a, if I take a slightly variation, I want a Kn local or En local. This generalized Moore spectrum, I can regard this category as a limit of this category. And then, like based on this setup, like to set up the 6 functors here.
As a limit.
Ah, sorry. Thank you. Yeah. Yeah. Does this answer the question?
Oh,
Or maybe not. So
it seems like a spectral generalization of some concepts I sort of am pretty familiar with about just representation theory. That's what all these things remind me. Like a sheaf on B of G, it might be a representation of G.
yeah,
And
yes.
these things are representation theory operations. And so I understand you're doing a spectral continuation
Yeah.
of them.
Yeah. And maybe also another question?
So you dualizing complex in your world, that's the adjoint representation sphere, or it's inverse, is that?
Like the
Whatever you twist it.
yeah, this one, yes, yes, is with a join. Yeah.
We were just speaking about compact groups before this talk, and there's this paper by Tim and Bauer where it's like a version of the adjoint representation sphere for these. Does it fit into your world?
Ah,
That's, I mean, it's Clausen's theorem, but that's the answer. It's not, formally it's something else. Clausen's theorem, but it actually is the adjoint representation. That's what he was referring to.
yeah, I think it's like there's identification. Like compare this one to the representation sphere with the.
Who's the other?
Well, I mean, this generality is Dustin Clausen.
Just Dustin Clausen.
Yeah, he's a recent treatment.
I don't think that's.
It's not available yet.
I haven't checked it out.
Circulating a document. I may have missed this. Is it
Yeah.
possible to describe the action of Gn on this sphere?
Yeah.
Yes, yes, yes. That's a theorem. Yeah.
That's the theory.
Yeah, the theorem is saying this is called the linear hypothesis. It's saying the action can be linear, can be identified with the linear action. The linear action is action on the Lie algebra on it.
The action on the Lie algebra is some representation of this group on a vector space of
Yes.
dimension n squared over the p-adic numbers.
Yes.
Is it? Yes, I'm really an outsider
No,
here.
no, no,
Is that
this
somehow like
very-
directly applicable to get an action on the sphere? Someone please educate me.
Yeah, it's a yes. Everything is P-complete. That makes solve the problem.
So it's surprising that you can start with a vector space in the p-adics and somehow get a representation of the p-adics and get an action on a p-adic sphere, but turns out you can do it.
This last.
But it's way not obvious.
Way not obvious.
And like I was really shocked when I heard about this myself, so I'm not surprised that you're shocked.
Oh, you're right. And then there's two kinds of actions I learned earlier in this conference. Is this a genuine action?
That's another
You're all Burrell.
Yeah, yes. Like, well, like this talk, you don't need to worry about the genuine for the top here. All the examples will in real, but you can do it. Oh, sorry, that's another name for naive. Sorry for the history. It's a little bit distracting of the names.
Maybe you should get your examples.
Yes. Yeah. So, right. Yeah. So maybe let me see like why this is something like you wanna think about, and these are a bunch of examples that is more familiar for the chromatic homotopy theory. So maybe yeah. Let's start with a rational case, so in this case. Yeah, Jared has this fantastic work showing, you can compute the homotopy groups after rationalize everything. And so this is Toby Bartu. Commercial length. and Nat Stapleton, and also Jerry Winston. So in this case, I can start with the most trivial case. I can do the trivial group. And if you do the trivial group now, you have no trouble with identifying the actions on the twins object, because the underlying, like from the previous discussion, is dimension n square dimension n square sphere. So in particularly, in this case, the transfer map is of the following format, which might be known as the algebra version by Strickland like a long time ago. So it's just this expression n times maps into the sphere. And then, so as you expected, if I do the rational case, so I can think about the unit elements on the left-hand side that maps to something in -n dimension. And this will be the volume form with the product of all the elements here. Because I'm doing the Poincare duality, and I just do the unit one to the volume form there. And now I can switch to other group. There is another either case. I can do the center of the whole group, which if you believe the action of the sphere is by a junction, so if I'm starting with something centered, then the action is still trivial. I'm still stay in this setup with this same number shift. Well, but now on left-hand side, you have 30 more interesting gadgets. You also have after Q rationalized, you also have an element in degree 1. And as you can imagine, if I start from the 1 doing the transfer, I'll get the element skip the first generator. And if I start with this element, I'll have the whole thing here. Yeah. The number is not the same. Oh, sorry, there's a missing one because this is one-dimensional. Thanks. Yeah. And maybe another more classical example is I can do the entirely similar story for the high 1 case. Now I can think about the determined map from this Morales letter group. And I can take the kernel. Let's name this as Sj here. So as you can imagine, you can have a very similar fiber sequence in this case. This is also the half sphere. And now you have a transfer in this case where this one actually gives the zeta 1. And well, this actually, even before rationally, you have a construction of a -1 elements in your Kn local sphere. Of course, like if you're trying to compute homotopy groups of sphere or some related gadgets, then the p torsion part is more interesting. So maybe the second case, so this is something rationally at least tell you this one detects something interesting. And maybe let's see what happens p torsion. So the reason for the title is I'm taking n equals 1, prime equals 2, or I can also take other primes from Ku instead of Ko. So as I said before, this is a due of the restriction, and this is just recover the image of J, but now like the J map is every construction is Kn locally, so this is a K1 local version of it. And then you move on to the next type 2, where computation becomes very complicated, but there's still maybe I should reverse the order since the large prime is easier. Let me just say, so in these cases, I can start with some more interesting for the small prime, it's harder. It's harder because the group contains a finite group of order not co-prime to P. So in particularly, maybe something interesting is this one, like also known as the K2 localization of the topological module forms. And there is an interesting, like, non-trivial twist by a representation sphere. However, it can be identified to an integer shift of this one. It's also, like, this is first due to Irina Bobkova, but also can be recovered in the identification of the dual for this one, where in the paper they also identify this one as the representative sphere for certain finite groups, including this case. So I have a map from this one to this one. And well, it just happens to be the same number in the prime 3 case. So, and like Mark Barris and Irina Bobkova actually show more than identify the spanning ideal, but they also show that if you are doing the so-called finite resolution spectral sequence computation, this dual map is a map in the resolution from the last piece to the original guy you compute. So this can be regarded as a H homomorphism in the finite resolution spectral sequence. So the last piece contributes to all the image of this transfer map. So that's something like not in the classical image of J. So maybe then, let me see the prime 5 case. So actually, I can see more names of elements. Or you can also see some, well, for this one, this one, like you can also see actual names, but it's quite challenging. But I will, let's see the name. Yes. Okay. Sven and Karamanov and Mark Mohoda carry out the finite resolution computation for I small p at prime 3. And in the appendix, there's a more, it's easier computation to understand the Fuller mode V1. So the computation is carried out in the manner of the duality resolution so that you can recognize the names to pin down the transfer maps, the image of it, at least in the case for this finite spectrum after mod P. And for the large prime, so maybe let not only, or first, the answer for this one, like for high 2, Shimura and Yabe did the computation, and Mark Barris has a fantastic reviewed paper, correct many mistakes, and make the results much more digestible. So you can read the computation for there. The difference is now the homotopy fixed point spectral sequence just collapse. So it's purely an algebra question. And then, as you can imagine, the transfer of the image goes to the top line. In this case, the height is 2, and the line is H4 of this one. So then, like we can see better than this one. Yingchuan has a very nice observation, saying that for safety, let's just ignore all the differential. Let's assume prime is much larger than the height n, so everything collapses. It's only an algebra question. And in this case, we know that the image of transfer contains the whole top line. Or maybe let me just say this contains this one. Every element in here is contained. So you're seeing, like, if you are doing when the spiral sequence collapses, when the prime is large, and everything in the top line in your homotopy fixed point spiral sequence is contained in this transfer of images. So it's actually a very non-trivial map.
You're doing transfer from the maximal complex group.
For this case, like, there's no trouble, right? For the previous two examples, yes, I pick up the maximal one, but there's no restriction. You can pick up the smaller one. You can even pick up something with positive dimension, right? Because before the example, I was missing shift by one, like for the center ZP cross. So you can, yeah, you have the variety choices. But in this case, yeah, I'm treating that one. And so in this case, I'm doing from this one, the trivial group to the K local sphere. Yeah. And well, so I think I should do one proof, but since there are 8 minutes, so let me draw the key picture, which is very beautiful, like I learned from Guchuan, and encourage you to finish this exercise, seeing that in this case actually it's subjective. Yeah. So the way to consider is you consider, well, in this case I also need, knowing this E is a pro-Galois extension from the unit, and I also use the identification for DE as E tensor some invertible objects. So I can think of a diagram. You can think this as a Gn times Gn equivariant, where you have the first Gx on this one, the second Gn on this one. And this is a home from E to, maybe let's drop E everywhere, to the unit 1. And the unit 1 can goes to E at the unit map. That's an induced map here. And you can show this is G1 times G1 equivariant, where you just put a trivial action as 1, have the trivial action on it. The point is, so from the bottom line, I can recognize this one as a dual of the restriction, where on the top line, you can compute this one easier. So you use the fact this is a pro-Galois extension. So this is some free coefficients. You apply the Gn fixed point on the whole thing, and then on the top, in the coefficients for this homotopy fixed point spiral sequence is something with free Gn action. So it has only zero homology, and by the Poincare duality, it must go to the only non-trivial thing on the left source is the top line. And since on the bottom, on the homology, this one maps to orbits, that is surjective. So by the Poincare duality, on the top line is also surjective. Sorry, I rushed a little bit, but in the end, I want to say why this is something like some of the equivalent homotopy theory computation in chromatic homotopy theory actually helps this kind of computation. So now let's think in the special case. I only want to work with.
Was your argument that the lower root calculates the transfer?
Yes.
And you calculated the upper part, and then I would assume the conclusion was the opposite, namely that the image is contained in the upper homotopy.
Yeah. Yes. I think I skipped some key steps, so make it confusing. I'm sorry. So I also need an identification for this one.
But is your conclusion that the image is contained in the top filtration, or is it fully contained?
The other way.
Thank you.
Sorry. Yeah, maybe I said the wrong way. Okay. Now, let me just fix to the group to be a finite group case. In this case, as I explained from the very beginning, I do have this map, and now maybe this is just a rectilinear sphere, and but like I can restriction to just as a H rectilinear sphere. And this is a map. And what's new is I want to emphasize on the left-hand side, at least for prime 2, like there are much more computations for all heights and many various finite subgroup after Hill-Hopkins-Ravenel's proof, because essentially they did enough computation for E4HC8 to deduce their result for the non-existence for larger covariant invariant. So in this case, like Juan Moreno, who is also in the audience, has a beautiful work identify this representation into a much familiar one. This will be for the group, cyclic group of order 2 to the power n. This will be some copy of regular representation of Z 2 to the n minus 1, where this one is as a quotient group. So then the representation can be also regarded as a representation of the Z to the 2 to the n representation, and that representation appears here. There are many copies, depends on the heights. You just match up the n squared dimension. So in particular, moreover, because with the Hill-Hopkins-Ravenel, the equivariant method, much more is known about the ROG periodicity for these guys. And in particularly, using those knowledge, you can shift this, much of the cases can be shifted back into the integer case. So in this paper, he did, in addition to the previous known, also you can do this one for height 4 and 8 for Z mod 4. So the suspension is 44. Sorry, this is minus 16. This is minus 46. And then, of course, you can shift to a periodicity, which these two, the periodicity is also known. This is 128 periodic. This is times 4 periodic. And you can even do the case like height 4 Z mod 8. So the Spaniard I do is a shift of, I think it's 112 of itself. In this case, like in the proof, Hill-Hopkins-Ravenel show that it's 256 periodic. So I'm seeing that, like you see a lot of elements, periodic families there, like, just from the computations. Yeah, so for the general, for the periodicity here, ROG periodicity, so in a joint work with 志鹏段 McHale, 宇涛流 and 丹尼石 国珍毛 and 周立徐. Well, Danny gave a talk like 3 weeks ago on this one. So we actually know in the prime case, including the Q8, not only for the CK group, but also for all possible 2 groups in there, we know the ROG, bunch of ROG periodicity there. So, and also we know the integer periodicity for it. So for each construction, you do have a family because they are periodic. So, and moreover, this transfer map deduces a map for spectral sequences. So in particular, you can deduce differentials where you know how to compute for finite groups into the profinite case. And the easiest case is you just see the height 1 case, you see the D3 to be the transfer D3. All those copies with zeta in their names. Yeah. But for height 2, prime 3, you can also see the D5, D9 will be transferred into the computation for the whole group. And so I'm minus 30 minutes. Let me just see. So one last sentence. If you read Oka and Shimomura's paper, you can identify some products of beta families in the image of transfer, which is non-local. So it does not only detect some periodic families in the local case, but some of them do live to the non-local world. And that's it. Thank you.
Before we take questions, can you complete the sentences there? DEH, maybe just one of them is good enough. Okay.
Yes. Yeah.
Okay, are there questions from the audience?
So back in prehistory, which means sort of before 1990, there was a lot of work done interpreting the image of J in terms of the image of the circle transfer and then the double circle transfer. And one of the things that was known was that the single transfer lifts to the first stage in the chromatic tone and the double transfer lifts to the second stage. And that doesn't continue, but I just wonder, I mean, can you relate these transfers directly to the localizations of the classical chromatic tone? I mean, are there maps one way or the other?
Now, maybe some audience know, but like the one point to emphasize is this construction works for all heights, so it does not stops at height 2. And in particular in large prime to see the non-trivial image. So that is the one difference between these two constructions.
I'm just curious to know whether you can sort of interpret things you're doing relative to what was done 40 odd years ago. I mean, certainly a lot was known about things detected by K2 under the double transfer. But how it relates to this, I'm not too sure.
I don't know, this is a very well guess. I didn't think very carefully. So there are a lot of CP in the, at least in the Morales-Valeder group, if I only think about the coefficient part. So that sounds like some circles there. And I can transfer from these subgroups too. I don't know what the image will be. I only know the center case I present. But like you have more copies in higher heights. And so maybe you can, like height 2, you have 2CP there, and you can do the transfer from that. I didn't compute anything in that case.
So a question related to the thing you just mentioned is, like, I guess I was trying to imagine, with this shift, if I understand the shift correctly.
Yeah.
So like this, with the finite groups, you're seeing stuff in the top cohomological dimension. The top, kind of the top virtual cohomological dimension kind of thing.
Yeah.
And so as you increase the dimension of the group, it brings you down from that. So like, I wonder if you could use a two-dimensional group and hit the 2 line and say that n equals 2. And
that's what I was really asking about.
Like
Oh, okay.
Okay. Question, seeing the classically transfer.
But maybe it's a little different, or maybe
it's like co-dimension. I mean, the example he had with this G and there, he was getting the -1.
I have the fortunate case that I'm thinking in n equals 2, the codimension and the dimension will be the same. So even if I don't have it right, it's still as applicable. I guess the one thing that I find interesting, Andy, is you're talking about the circle transfer, right?
Yeah. Well, or the double circle transfer.
Yes, and the double circle transfer. But these are transfers associated to Lie groups, so like classifying.
Well, that's something else I was going to ask. But yeah, I mean,
but this is something like this is like in the profinite Galois direction, like kind of opposite.
Yeah, except that, I mean,
I'm gonna interview
historically,
I'm sorry. The referee has. Cards have been issued.
Any questions, more questions which are not resurrecting history, but directing. If not, let's go to lunch.
Thank you.